welcome to the deep dive. Today we're really getting into the foundations. We often talk about AI, machine learning, all the flashy code.
Right, the algorithms themselves.
Exactly. But underneath all that, there's this, well, elegant mathematical structure.
The real engine room.
Yeah. So our mission today is to unpack what we're calling the trinity of math for data science: statistics, calculus, and algebra. And crucially, why they matter, not just as theory, but practically.
And knowing this trinity, that's what lets you really innovate, I think. You move past just plugging things into libraries.
You actually understand how it works.
Precisely. How and why. That's the key to building something new, or even just properly troubleshooting what you have.
Okay, so let's start with the first one. Algebra. You called it the language of data. What does that mean in practice? Like if I have data points.
Right. So imagine your data, say, features of a house, square footage, number of bedrooms, age. Algebra gives us the tools to represent that. A single house, that's often a vector, like a list of numbers.
Okay, one list for one house.
Yeah. And then if you have, hundreds or thousands of houses in your data set, you stack those vectors up.
And that becomes...
A matrix. Rows are your houses, columns are the features. It's a really neat way to organize everything.
But it gets more interesting, right, with things like matrix multiplication. I hear that's huge in deep learning.
Oh, absolutely huge. It's not just tidy organization. It's the computational workhorse. It's how layers in a neural network talk to each other, how transformations happen.
So why is it so fast compared to, say, looping through data?
Well, that's vectorization. Your computer's processor, especially GPUs, are built for this. They use something called CMD, single instruction, multiple data. Meaning they can do the same math operation, like an addition or multiplication, on many different data points all at the same time, in parallel.
Instead of doing them one.
And by one.
Exactly. Forget for loops for this kind of scale. Vectorization is dramatically faster. It's honestly what makes training massive models even possible today. Got it.
And if you want to understand how these deep networks work, you have to realize data points are never just isolated numbers. They're organized.
So they're like collections of numbers.
Exactly. They're vectors in this massive high-dimensional space. That n-dimensional reality where AI operates, it's the map of the world for the model.
And that map gets really complex, right? I mean, when we move into modern systems, things like video processing, we're not just talking about vectors anymore. We go way past matrices into these higher order tensors.
Yeah, think about a standard RGB image on a screen. You might picture it as a flat grid of pixels, a 2D matrix. But it's actually a rank 3 tensor. It's got height, it's got width, and then it has that crucial third dimension for the red, green, and blue color channels.
So without that third dimension, you'd be losing all the color information, all the context.
You'd be losing almost everything. And to handle these huge structures, you need some serious algebraic power tools. You need decomposition.
Which is just a fancy way of saying we need to break these things down.
We have to. And arguably the most powerful tool we have for this is singular value decomposition, SVD.
Hold on. I've heard SVD can be pretty computationally intense on its own.
Yeah.
So are we just shifting the problem around? What makes it worth it?
Because SVD is like AI's compression artist. It gives us a mathematical guarantee. It finds what are called singular values, which measure the energy or the really critical information in the data.
Okay, so it finds the most important bits.
The most important bits, which means we can get the absolute best low-rank approximation.
So what does that practically mean for, say, a large language model?
It means we can actually deploy it. We use SVD to compress the weight matrices of these LLMs. You can often throw out over 30% of the information and still keep almost all of its reasoning ability.
Wow, that's huge.
It's the only way to make it feasible to run.
All right, this is where it gets really fascinating for me. Okay, so algebra gives us the structure, the language. What about statistics? You framed it as the grammar of insights.
Yeah, if algebra organizes the words, statistics helps us understand the meaning, the story the data is telling. It deals with patterns, relationships, and crucially, uncertainty.
Right. I know, maybe not the most thrilling word, but honestly, it's the bedrock, the compass guiding everything in AI and machine learning.
It really is.
Our plan is simple. Take your sources on stats and ML, pull out the absolute must-knows, and basically shortcut your path to really understanding this stuff. Let's maybe think about it like we're building a customer churn model. Stats is our guide.
That's a great way to frame it. And what's really fascinating is how statistics takes all that raw, messy data and turns it into something reliable, something interpretable.
Right.
It's what makes an AI system trustworthy, not just predictive. It gives us actual confidence, say, in those churn predictions we're making.
Okay, so it's like a universal language then for anyone working with data, whether that's healthcare, marketing, whatever.
Exactly, a common ground.
So let's unpack the main branches. I gather there are two. How do they work together?
Yeah, two main ones. And critically, they aren't really separate things. It's more like a cohesive feedback loop.
Yeah.
You've got descriptive statistics first.
Okay.
That's all about summarizing the data you know. So for our churn example, think calculating the average age of customers who churned or the variation in their contract lengths, the mean, the variance, that sort of thing.
Just describing what's there.
Precisely. Then inferential statistics comes in. It uses samples like our historical churn data to make, reasonable guesses or predictions about the bigger picture, the unknown population of all our customers.
Making the leap from the sample to everyone.
Exactly. And here's the loop. Say our descriptive analysis shows the churn data is really skewed, maybe lots of very new customers leaving. That insight immediately tells us, okay, be careful. We probably shouldn't use certain inferential methods that assume data is nicely balanced, normally distributed.
Right. So it guides the next step.
It guides us towards maybe transforming the data first or using different kinds of statistical tests that don't rely on that assumption. It's synergistic.
Got it. So descriptive stats really kicks off our understanding. It's the core of exploratory data analysis. EDA, right? Revealing things like central tendency mean, median, and how spread out the data is standard deviation.
Absolutely. Think of it as your first diagnostic tool. It flags potential data quality problems before they mess up our churn model.
Like finding errors or weird values.
Yeah, exactly. Things like kurtosis, which tells you if your data has fat tails, meaning lots of extreme values, or the inner quartile range, the IQR, that maps the middle 50% of your data. These are great for spotting outliers because they aren't as easily fooled by those extreme values as, say, the simple mean is.
Okay, so it helps clean things up.
Definitely. And that leads to practical steps. Like if you have missing age data, maybe you fill it in with the median age, which descriptive stats help you find reliably. Or using z-score standardization that's scaling features so they all contribute fairly to the model. Or maybe a log transformation if your data is heavily skewed to make it behave better for certain algorithms.
Okay, that makes sense. So we use descriptive stats to understand and prep the data. Now, building on that, we move into inferential statistics, using that feedback loop you mentioned. The goal here is generalizing, right? Making sure our churn model works on new, unseen data, not just the data we trained it on.
Precisely. Generalization is key. And often, people just report a single accuracy score for their model, like 90% accurate. But inferential stats gives us better tools.
Like
Confidence intervals. Instead of just saying 90%, maybe we find a 95% confidence interval for our churn model's accuracy is, say, 88% to 92%. That range gives a much more robust and honest picture of how reliable that model likely is in the real world.
a range of possibilities. I like that.
Yeah. And this is where it gets really powerful, I think. Inferential statistics brings in hypothesis testing. It's basically the scientific method applied to machine learning.
Okay, how does that work?
Well, you start with a default assumption, the null hypothesis, or H0, H dollars. This assumes there's no effect or no difference. For our churn model, H dollars might be customer age has no impact on churn.
The status quo, kind of.
Kinda, yeah. Then you have the alternative hypothesis, H1, H$1, which is what you're actually trying to claim customer age does impact churn.
Okay.
Then you look at your data and calculate a p-value. The p-value tells you the probability of seeing results like yours if the null hypothesis were actually true.
Okay. Probability of the data if H0 is true.
Exactly. And if that p-value is really small, usually less than a threshold called the significance level, often 0.05, it suggests your observed data is pretty unlikely under the null hypothesis. So you reject H$, in favor of H$1.
So you'd conclude age probably does impact churn.
Correct. It's super useful for formally validating which features are actually important for your model, or for A/B testing comparing two different versions of your churn model, maybe using something like a t-test to see if the performance difference is statistically significant, or if it could have just happened by random chance.
That sounds incredibly useful, but also like something you could easily misuse. Which brings us to statistical rigor. and potential pitfalls. You mentioned statistical significance. Is that the same as being important in the real world?
Ah, great question. And no, absolutely not. That's a huge pitfall. Statistical significance having a low p-value just means the observed effect is unlikely to be due to chance. It doesn't automatically mean the effect is large enough to be practically significant or meaningful in a business context. You might find a statistically significant difference that's actually tiny and irrelevant.
Okay, so don't just chase low p-values.
Definitely not. And another big one is misunderstanding the p-value itself. A p-value of 0.05 doesn't mean there's a 5% chance the null hypothesis is true. Remember, it's the probability of the data, assuming the null is true. Subtle, but important.
Right, the condition is key.
And then there's the multiple comparisons problem, or sometimes called the multiplicity mess. Basically, if you run lots and lots of statistical tests purely by chance, you're going to get some statistically significant results, even if nothing real is going on.
Like testing dozens of features for the churn model.
Exactly. Imagine testing 20 features where actually none of them truly affect churn. With that standard 0.05 significance level, you'd still have roughly a 64% chance of finding at least one feature looks significant just by random luck.
Yeah, okay. That could lead you to put useless features in your model.
Precisely. It contributes to overfitting, building a model that learns noise instead of the real signal. That's why it's crucial to also report the effect size. This tells you the magnitude or strength of the effect, not just whether it exists statistically. It gives you that practical perspective.
Okay, so p-value plus effect size gives a fuller picture. It seems clear then that descriptive and inferential statistics really work hand in hand. You need both for solid data science.
Absolutely indispensable. From that initial look at the data with descriptive stats, right through validating your final churn model with inferential methods, statistics ensures integrity.
So it keeps everything honest from start to finish.
Yeah. So what does this all mean for you listening? I think mastering these statistical foundations is what really separates someone who can just use ML tools from someone who's a true expert.
Building things that actually work reliably.
Exactly. It lets you build models that aren't just performant on paper, but are genuinely robust, reliable, and crucially interpretable. And that really shapes the entire future of trustworthy AI. So maybe consider, how does applying this level of statistical rigor change how you approach your next data project?
Makes perfect sense.
Right.
Okay, Trinity Part 3. Calculus, the engine of learning. Why engine?
Because calculus is fundamentally about change, how things change in relation to each other. Think of your car's speedometer. It's showing the rate of change of distance over time. That's calculus.
So how does that apply to a model learning?
Well, models learn by adjusting their internal parameters to get better predictions. Calculus helps us figure out how to adjust them efficiently. We start with differentiation. For one variable, the derivative tells you the slope, the instantaneous rate of change.
Like how house price changes just with square footage.
Right. But models usually have tons of variables. That's where the gradient comes in. It's like a multi-dimensional derivative.
A compass.
A compass, yeah. It points in the direction where things are changing the fastest, usually, where the model's error is increasing most steeply. Imagine you're blindfolded on a hillside. The gradient tells you which way is straight uphill.
Okay, so if the gradient points to where the error gets worse...
You go the opposite way. And that's the core idea behind gradient descent.
The ball rolling down the hill analogy.
That's the one. You calculate the gradient of your error, take a small step in the opposite direction, recalculate, take another step, and repeat. You iteratively roll down the hill towards the point of minimum error.
And models use this constantly during training.
Constantly. A key example is backpropagation in neural networks. It uses the chain rule from calculus to efficiently calculate how much each connection in the network contributed to the final error.
So it knows exactly how to adjust everything.
In a very clever, calculus-driven way, yes. It distributes the error signal backwards through the network.
Wow. Okay, so bringing it all together quickly for our house price example.
Yeah.
Algebra structures the house data in matrices.
Yep.
Calculus, through gradient descent, finds the best settings for the model by minimizing the prediction error.
Right. It tunes the engine.
And statistics tells us how good the predictions are, measures the uncertainty, and validates the whole thing.
Exactly. They're completely interwoven. Algebra provides the language, statistics, the grammar for understanding, and calculus the engine for learning and optimization.
A really powerful combination.
It truly is. And understanding that interplay, the why behind just running the code, that's where real mastery lies. It's about building AI you can actually trust because you understand its foundations.
So, a final thought for everyone listening. If you move beyond just using the pre-built tools and really grasp this mathematical bedrock, what currently complex problem could you start to genuinely tackle? Something to think about.